This is the title of my poster, An Equivalence of Three Butterflies in Lifshitz Background. So in this work, we have computed the Lyapunov exponent and butterfly velocity in this Lifshitz background, and we have employed these two methods of chaos computation. And we'll check whether these two methods are giving the same results or not. So though there are many proposed methods of chaos computation, but this double commutator gives this exponential growth. And so this quantity tells basically how an early perturbation P affects the later measurement of W. Here, let's discuss this Lipschitz black hole background. So one can achieve this D plus one dimensional Lipschitz black hole solution by adding a gas field coupled to the gravity in the action with some, and these are some negative cosmological constant solutions. And in asymptotes, these black hole solutions have some fixed point geometries. So at the boundary theory, these are some critical point at the phase transitions. And these points are invariant under this space-time invariance. So for this entanglement wedge method, so let's consider this z equal to 0 is the boundary and z is the horizon. So now releasing a particle, so basically when you perturb this boundary thermal dance means you are releasing a particle near to the boundary and it is enclosed in the RT surface. So as time is evolving, this RT surface is approaching the horizon, and this velocity at which this RT surface is approaching the horizon is the butterfly velocity. And we can calculate it from the Rota-Kanagi equation. And the Rota-Kanagi equation, we got it by varying the determinant of the induced metric with the radial coordinate. And solving this RT equation, we get this butterfly velocity, and this is dependent on the anisotropic index. By putting J to be 1, we get the standard ADS D plus 1 black hole results. So for this OTOC computation, we go to the cruise scale coordinate and write the Lipschitz metric in this coordinate. And here, if equal to 0 is the horizon. So now when you release a particle at like asymptotic at like past boundary, and the particle, the observer who is at t equal to 0 slice will see the energy of the particle is like exponentiating. So we can write the stress tensor of the null pulse which will be localized at the p equal to 0. And because of this null pulse, there will be discontinuity in continuity at the equal to 0 horizon, and we can write this discontinuity in this way. Then again, from the backreactive metric, we can calculate the stress tensor and solve the Einstein equation near the horizon. So solving the VB component of the Einstein equation near the horizon, we get the shock profile, and this is of exponential in form. Then I calculate the Lyapunov butterfly velocity from the shock profile, which matches with the previous result. And for the pole skipping, now we just define the retarded Green's function, which is just the ratio of the subleading to the leading coefficient of the bulk ingoing solutions near the boundary. And at the pole skipping point means at some frequency and momentum, this resource response and source both are 0. So these are basically some points in the momentum space where the line of poles and zeros are crossing each other. So here the Green's function not a well-defined thing, and this is a connection to chaos when you part of the sound modes only. Okay, so here in the Lipschitz background, by doing this pole skipping analysis, we get this Lyapunov and butterfly velocity, which matches with the previous two methods. So now for the iconal phase, we write down the bulk phase shift, and from the null geodesic equation, we can calculate the iconal phase. Here near the boundary, this iconal phase is like inelastic, and near the horizon at high energy limit, it is elastic. At low energy limit, it is again inelastic. And from the geodesic instability also, we can write down the Lyapunov exponent, and we check that it is positive only when the second derivative of the potential is negative, means the orbit is unstable. And this Lyapunov exponent is equal to 2 pi t only at some specific value of chi. Okay, thank you.